Series and parallel circuits. Two key ideas, two key terms. If any of you get into electronics or become an electrician, you want to know, hey, is this a series circuit or a parallel circuit? And thankfully, the words mean what you expect. A series circuit is a circuit where resistors are connected in a row with no junctions between them. Which circuit shows resistors in simple series? The top one or the bottom one? Example 2 says, find an expression for the total resistance of a series circuit. There is a lovely proof, and had we not started the year late, I'd do the lovely proof. I'm just going to give you the punchline. You know what? If this was 3 ohms, and this was 5 ohms, and this was 7 ohms, where'd the 15 come from? Turns out, if they're in series, our total is add the first resistor, add the second resistor, add the third resistor, add the fourth resistor, just add them up. Which, Jeff, you can't really ask for much of a nicer rule than that. Okay. It comes out of the fact that all of them have the same current, right? And I can show that all of them have to add to my source voltage, and if you do some algebra, suddenly you'll find, oh, the equivalent resistance is add them all up. In fact, let's put it in a box here. If we're in series, our total is R1 plus R2 plus R3. This is not on your formula sheet. This you'll have to memorize. You know what, Jake? Do the homework. You'll memorize it. Don't, and you'll have to go out of your way to memorize it. So example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. Now, do you remember what I said the first thing we always looked for? Total current. You notice now there's no current given anywhere. Do you see an amps anywhere, Darren? No. So now we're going to identify what kind of a circuit is this. These two resistors are in series. So this is mathematically equivalent to a total resistance of what? In fact, Anthony, here is the mathematically equivalent circuit, and we're going to redraw them sometimes, and sometimes we'll do them in our heads. We have a 100-volt source, and it's the same as one 25-ohm resistor. Mathematically, those two circuits are equivalent. In real life, they're not, but mathematically they are. What's my total resistance, Jake? What's my total voltage source? What's my total current? Do the math. First of all, we're going to use Ohm's law. Ohm's law was what? Really? You're having to get a calculator out? Put your calculator down. V equals I times R. Darian, get the I by itself.
Divided by R.
Darian, what's 100 divided by 25? That means the current leaving right here is 4 amps. That means the current leaving right here is 4 amps. I really don't care about that. Riley, what I care about is, folks, what's the current in this 5 ohm resistor? Tawny, 4 amps. Oh, what's the voltage in drop in this 5 ohm resistor? What do you get? Please go I times R. You know the I, you know the R. What's the voltage drop? 20. Darian, how high? How many volts? What do I lose?
20.
Leaving?
80.
What must I lose going through there?
20.
How high?
100.
What do I lose?
20.
Leaving.
80.
And if there's only one more hill and I get to, what?
80.
Okay, now we can use that with Kirchhoff's laws, but now we can also prove it another way, because what's the current in here, folks? Still 4 amps. Using I times R, what does the voltage have to be in there? And that's really what I would do as my proof for why this works, because it gives you the same answer both for Kirchhoff's laws and by using Ohm's law, Ohm's law, Ohm's law, Ohm's law, Ohm's law. Now let's answer the question. The question said, select the best answer for the voltage drop across the 20 ohm resistor. 100, more than 50, or less than 50? What's the best answer, A, B, or C? In fact, I can be more specific. Not only is it more than 50, it's exactly, there's my proof. A new strategy we're going to add then, Ben, is if they give me a complicated circuit and no current, I'm going to rewrite it as its mathematical equivalent, one resistor, because one resistor and one voltage source, I total, is going to be V total over R total. And if I find the total current, Anthony, the question falls apart. Example 4. It says find total resistance and current, and then find the current through and the voltage drop across. You know what? We're going to find everything. We're going to find the current in each resistor, the voltage in each resistor, and just for giggles, let's find how many watts each bulb is. I would start out looking for total current. Do you see amps anywhere? Now, as my intermediate step, Sarah, I identify what type of circuit this is. This is a series circuit. So I'm going to say, what's the total resistance here? And I'll write out my work in your homework. If you go straight to the answer, great. But just so we know what we did, I'm going to write 15 plus 5 plus 5. In my head, Jeff, I'm going to get. So the mathematically identical circuit, 100 volts as my source. Jeff, you're telling me I can, by the way, I'm not even doing a proper circuit sketch. I really should go, don't write this down, I really should go like this and then label that as 25. Oh, you know what? This is my rough work. I'm so lazy, I often just put the 25 ohms as a number right there. Whatever works for you, but that's me even saying, I'll even draw the squiggle lines. What's the total voltage source, Jeff? So here's what Darian said earlier. He said I equals V over R. You know what? I total is going to be V total over R total. And if I haven't mentioned it already, it's worth mentioning. If you know the total current, the question's going to fall apart. It's going to be 100 over 25. Unlike Darian, Jeff, you don't need a calculator to do that one in your head, do you? How many amps? You started to. Why is that so helpful, Jeff? How many amps leaving? This is total current. That tells you how many amps leaving the battery, the chairlift. I don't care really about that. What I care about is follow it, follow it, follow it, follow it. How many amps in this resistor? How many amps in this resistor? How many amps in the next resistor? And now in every one of them, do you know 2? Then you know 4 things. All coming together? How many volts do I lose in this first resistor? 60. In this second resistor, 20. In this third resistor, also 20. How many watts of power do I use in that top resistor? V times I. 60 times 4. It's a 240 watt bulb or appliance or whatever it is. Power loss here is V times I. Now, the most common mistake I see here is sloppiness. Kids are doing this so fast, they'll multiply the wrong things together. Look at your units very, 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 very carefully. In fact, you saw I did that a couple of times last class when I was on my roll doing all the math in my head. There was one such, I used the wrong thing. Don't do that. V 20 times, you know what? 80 watts, and I think this one's also going to be 80 watts, yeah? Whatever 2 you give me, Cole, I can find the other 2, and now you actually don't even need to give me 2 if I can rewrite it as its mathematical equivalent. I can start there and find the 2. Turn the page. Second type of circuit. Sadly, Noah is a little more difficult, but also way more common. It's called a parallel circuit. And that's a circuit where resistors are starting. You know what? Actually, let's just do this. Cross out the word R, where resistors start and end at the same voltage, same height. In other words, it says, which circuit shows resistors in simple parallel? This one. Because it looks like everybody, come here, it looks like everybody shakes hands right here. Some go this way, some go that way, some go that way. Do they all go down one resistor? Do they all start at the same spot and meet at the same spot eventually without going through any other resistors? Those are in parallel, simple parallel. Now, these two are in series with each other. In other words, if I wanted to, if this was 2 ohms and this was 3 ohms, I could just think of that as one single, how big? 5 ohm resistor. And if I did that, this resistor here is in parallel with this mathematically equivalent 5. We're going to get there. But you can start to break circuits down and rewrite them and rethink of them into their simplest mathematical equivalent. And it's all about trying to find total current. Example 6 says, find an expression for the total resistance of a parallel circuit. Again, there is a lovely proof, but I'm just going to give it to you. If I call this R1, if I call this R2, if I call this R3, you have to recognize, Riley, that they're in parallel. And it turns out you can't find the total resistance. All you can find is 1 over the total resistance. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over. Here, you are going to need to use your calculator. So get them out. Because I'm going to show you a nice shortcut method, actually. A button that every scientific calculator has that you may never even have noticed or used, and it turns out to be a wonderful time saver for this unit. So in the box, parallel R total, actually it's 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5 plus 1 over R6. Example 7. Find R total, I total, and then V and I for all resistors. By the way, are you okay that if we know V and I, we can always find power by going V times I? You guys are okay with that? I'm going to stop finding the power every time because it just clutters up our diagrams. But if you know 2, you know 4, I'm going to go, if you know 2, you know 3, and the 4th one's kind of redundant. Okay. Did they tell me current anywhere? No, I would look for that first. What type of a circuit is this? These are 3 resistors in parallel. Okay? So, 1 over the mathematical equivalent, the total resistance, is going to be equal to 1 over 10 plus 1 over 15 plus 1 over 20. And here is how, I mean, I'd like you to find common denominators and forget it. Here's what you'll type. 1 over 10, 1 divided by 10, plus 1 divided by 15, plus 1 divided by 20, and you're going to hit equals. Most common mistake, kids think that's the total resistance. No, we found 1 over this. I need to take the reciprocal of this. Now there's two ways to do this. There's the long way, which is to type 1 divided by answer button. There's a better way. All of you actually have a reciprocal button. If, now that you have your answer on your screen, you hit your little x to the -1, that actually means flip the answer. And it's way less typing. Oh, and hit equals. This is the same as a 4.615. You know what? I'll go 4.615 ohms. I'm going to be really technical here. Tani, what have I written right here? Read me the whole thing. If you now put an equal sign and said 4 well, no, they're not, because we flipped it on our calculator. So what I usually do is I draw an arrow. That's my way of saying I've done some work. Our total is 4.6154. Put your pencils down, look up. Don't write this down. What we're saying is this is the mathematical equivalent of a 60-volt source and a single solitary 4.6154 ohm. We're saying those two circuits are mathematically identical. But you know what, Jeff? I'm kind of tired of redrawing these. You can, if you want to, pick your pencils up and write that. But I'm just going to say, you know what? I got our total. What's the total height of this mountain? 60. You know what? I total equals V total over R total. What's the total current in this particular circuit? 60 divided by 4.615. 60 divided by answer button. Nice yawn. Oh, worked out evenly. Kind of nice. How many amps are leaving the battery? And since they did want me to find I total and R total, I should probably put boxes around these. So found that, found that. Does that mean 13 amps here, 13 amps here, and 13 amps here? Don't write this down. Is that? Darian shook his head. He's correct. That's wrong. Because that actually, now you're telling me there's 39 amps. Because that's what would flow together right there. Right? Okay. I know total current. Do I know current anywhere else? Say no. Is there anywhere else with two pieces of information? Say no. Let's go skiing. Ready, Anthony? How high? It seems to me that you can go down just this resistor and get to the bottom. How many volts must we lose going through that resistor then? Do I know two things? Ding, ding, I know three things. I know four things, but I said I'm going to forget about finding power. How many amps must be going through this resistor? Oh, I can do this one in my head. 6. Leaving, I think, 7 more amps to play with through the other 2. Right? Anthony, let's go skiing. In fact, you could also say, hey, Dueck, this, and these 3 resistors, these 3 voltage drops have to be identical because we split up and met up. The only way you can do that is if you go down the same height drop, the same voltage drop. So it's 60 volts and 60 volts. Do I know 2 things? Well, current here, 4 amps. Current here, 3 amps. Double check. Does that give me my 13 amps? Ta-da. Oh, could I find the power in each of them? Sure. This one here is 60 times 360 watts. That there is probably like a, you don't call them ghetto blasters, stereo. 240 watts. Not a light bulb, some kind of an electric appliance. 120 watts, could be a bright bulb.
My mom says I'm a bright bulb.
No. Okay. 180? Oh, sorry, I did the same thing. Multiplied the wrong, good gosh. 180, yeah. So in terms of power loss, you would be losing 360, 240, whatever the heck that's how many watts would be flowing through this particular circuit. And do you remember what I said tends to trip a breaker in a standard household circuit? How many amps? You remember? 15. This is close to tripping the breaker. Plug one more thing in here, probably in trouble. Example 8. What can be said about the voltage drops across the resistors in the circuit below? Did they tell me total current? Yeah? Cool. Then this question should fall apart. Did they tell me the battery, the height of the mountain, the chairlift? Ooh, you know what? I'll have to figure out how high the mountain is by doing a ski run eventually. Always going downhill. You may recall last day. Oh, sorry. Is there anywhere they told me 2 things? No? Well, I know total current. Seems to me I can find the mathematically equivalent circuit here. Now, these 2 are in parallel with each other. These 2 little guys are in parallel with each other. And these 2 little guys are in parallel with each other. You okay with that? One over R total equals 1 over 10 plus 1 over 15. What could I replace those guys with? A single resistor, how big? Now, another shortcut. You ready? You can actually go like this. 10 reciprocal plus 15 reciprocal equals reciprocal. That is 1 over 10 plus 1 over 15, 1 over the answer. What's this the same as? And you know what? Instead of calling T total, I'm going to call it top. So the top group of parallel is the same as that. 1 over R, I'll call it R for right, is 1 over 20 plus 1 over 5. What can I replace this right-hand resistor with? What's it mathematically equivalent to? And you need to practice this on your calculator. If you don't know how to do it, you need to figure it out. Four? You okay with that? I called this one R top. I called this one R right. I called this one R B for bottom. Okay. 1 over R B for bottom is 1 over 12 plus 1 over 12. I think this one I can do in my head because 1/12 plus 1/12 is 2/12. 2 over 12, flip it, 12 over 2. Should be 6. Double check me. Yeah? Okay. I've got to scroll down, but I left lots of room here, and you guys all have the numbers there. So here is the mathematical equivalent. I don't know the battery. But what can I replace that top group with? How many ohms?
6.
What can I replace that right group with? How many ohms? What can I replace that bottom group with? How many ohms? Sorry? 6? What can you say about those three resistors? Are they in parallel? No. What are they in? Add them up. What is the total resistance of this big uber circuit? That huge upper circuit can be replaced with one resistor. How big? And you may have noticed, or you may recall, that I mentioned if they tell me the total current, the question's going to they told me the total current was 5 amps in the original circuit. Oh, what can I find if I know R total and I total? The chairlift, the battery. V total equals I times R, 5 times 16, 80 volts. Let's go fill that in on our circuit now. Da 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 da. Ha ha. What can be said about the voltage drops? I can certainly tell you that's 80 volts. Okay. I can do even more than that. What's this the same as? 6 ohms. How many amps are flowing through this mathematical equivalent? 6 ohms, 5 amps, 6 ohms, 5 amps. $30 volts. And each hill has to be the same voltage because you shook hands, split up, and met up? Mr. Dueck? Yeah, Miller. Don't I now know two things? Why, yes, I do. How many amps went through that top one? 3. I think 2 went through the bottom one because we're splitting up 5, but let's double check. If I go V divided by R, do I also get 2 amps? So I've got multiple ways to get there now. Let's keep going. What did you tell me this could be replaced with? How many amps? Sorry, how many ohms? A 4 ohm resistor with how many amps flowing through it grand total? 5. 5 amps, 4 ohms. Each of these must lose 20 volts. Oh. 4 amps, 1 amp. Still adds to 5. Whew. I can be a bit more clever. Do you remember if the resistors are identical, what happens to the current? Should be 2.5 and 2.5. Let's prove it. Okay. Remember, I gave you all those. I said you don't need to know these rules. I gave you some rules last day, and I said they're kind of handy. And I could have solved this using those ratio rules. They're redundant. I can solve these using Kirchhoff's laws, Ohm's laws, in equivalent mathematical resistors. Oh, what was this the same as, Jake? And how many amps are flowing through it? Mathematically equivalent. But you know what? That must mean each of these is. Oh, there's another way I could have got this. Jake, do you ski? Let's ski. Ready? I'm always going to go downhill. How high? Take away 30, leaves. Take away 20, leaves. Got to be 30. I just verified that my other calculations must be right. There's no way I could have fluked into getting the right answer with Kirchhoff's law and Ohm's law. Or I could have gone down this path. Start 80, go through this one, lose 30, 50, go through this one, 20, leaves me with 30. No matter which path, as long as I keep going, Carl, downhill. Oh, by the way, have I started to convince you why it's so much nicer to pretend that positives move and not go in the negative direction? It's much more intuitive sense to me. Oh, what is 30 divided by 12? Is it 2.5 amps and 2.5 amps? Okay. That's why I said those ratio things from last day. Remember I talked about that? Really not that necessary to commit to memory. They're convenient. I could have seen that 12 and split it up, and I probably could have split up the 5 using the 20 and the 5. I could have split that 5 amps up into a 4-to-1 ratio as well. This is kind of fun. We're skiing. Here we are. Example 8, the one we just did, illustrates an important point. It says the voltage drop across parallel resistors, the voltage drop, Carl, will be identical. Not the current, unless the resistors are identical, but the voltage drop will be, and if you know the mathematically equivalent, you can do good stuff. In a household circuit, plugs and lights are wired in parallel to 120 volts. Alternating current, but what we're doing still works for alternating current. Each circuit has a circuit breaker, and that circuit breaker is designed to trip at 15 amps. Usually, there are a few 30 amp circuits, your stove, your dryer. When that switch or that breaker trips, it cuts off all the current. If you connect a 1500 watt hair dryer and the 500 watt TV to the same circuit, will we cause the 15 amp breaker to trip? Let's find out. You know what? Let's draw the mathematically equivalent circuit. Ready? What's our voltage source? 120. Now, don't write this down. This is the symbol for a battery for direct current. Is this direct current? So, turns out the symbol for alternating current is a circle and a little wave going up and down like the current. You do not need to know that, but nerd trivia. Okay? Sort of. I have one resistor here. I have one resistor here. No matter which direction we go, because now with alternating current, you're going uphill, downhill, uphill, downhill. Let's ski that way. How many volts must I be using up in that resistor? Nope. How many volts must I be using up in the right-hand resistor? Mm-hmm. Oh, what else did they tell me about the hair dryer? Yeah, say it. Careful.
Oh.
Hair dryers use a lot of water. They move a lot of heat.
Oh, 1200.
1200? Is it 1200?
Yeah.
Do I know 2 things? Well then, Darian, you know what? I know 4 things, and in particular, I'd like to find current. If you give me power and voltage, how can I find current? This is also why I said the other day, you don't need to memorize Ohm's law and Joule's law, but you'll get sick of looking them up. What was Joule's law? Power equals P equals, okay? So I equals what? P over V. How many amps must be flowing through this resistor? Oh, that works out nice. TV. What else did they tell me about the TV? How many amps must be flowing through this resistor? 1.6 or 1.7? 1.7? I'll go 4.2. Now, you'll notice I'm not drawing arrows on this because there is no official downhill on alternating current anymore, but I can tell you what the total current is. How many amps are flowing through this circuit? Are we going to blow the breaker? We're close. Don't plug anything else in. This won't trip the breaker, barely. In fact, if you have a lousy breaker or it's wearing out, it might trip it. Every once in a while, you get a breaker that's a little more sensitive and needs to be replaced. Almost started writing on my screen with this one. That would have been a problem. Whoops, picked up the wrong pen. Darian, what did you say? I total equals what?
14.
So, just barely safe. I'll bet you a 600-watt TV would blow the breaker. Household circuits. Now that's alternating current. Let me emphasize again, Carl, I will not be asking you an alternating current question on your test, but since your houses have that, I don't mind doing it as nerd trivia. And I think we analyzed it using Kirchhoff's laws anyways. What's your homework? More practice. Oh, by the way, the next lesson is series and parallel circuits combined. We'll start looking at circuits that have some series and some parallel, and you rewrite each little mini chunk, and eventually you'll end up with several series in a row and add them up. There's our eventual goal. For now, I think you can do, need to practice this, number 1, number 2, number 3, number 4. Ask me to go over number 4 next class because I don't think there's an answer. Are there answers for number 4? No. Forgot to add that. 6, skip 5. I may come back to 7. I can't remember how much I have here for practice. 8 is good. By the way, 7, look up, go back to 7 for example for a second. These would be great using principles of physics right to explain questions, but instead of saying find the total current, make all of these light bulbs, and then part B would say, what if you pull the 15 ohm bulb? Which is the brightest bulb now? Or what if you add another light bulb? What's going to happen to this bulb? Brighter or dimmer? Whenever I'm talking about brightness, what am I talking about really? Power. Okay, 8 is good. And household circuit number 8, 10 is good. 11 is good. 13. 14. 14 is going to turn out to be very important. I haven't talked about it, but it has a huge impact on electronics. You also, if you haven't yet, you got lots of time. You should leave today probably completely caught up in this unit. Right? So you're getting, holy smokes, a lot of time. Of course, I also have a cool video to show you.